Hey everyone. This is the final topic we're going to be talking about this semester. This is in chapter 6. It's about orthogonal vectors. And if you've taken Calc 3, some of this you've already seen, so it won't be much of a surprise, although we're going to take it in a different direction than you took it in Calc 3. And so here's the basic definition. It's about the inner product, also known as dot product. Usually you call it the dot product in Calc 3. And the way this works is you take two vectors in Rn, and when you do the dot product or the inner product of these two things, you end up with a vector or a number in R, just a real number. And the way you do this product is you just multiply the corresponding entries together, u1, v1, u2, v2, un, vn, add them all up, and you just get a real number. So we can do a quick example. If I take, for example, 1, -1, 2, and 3, 0, 1, then when I do their dot product, I have 1 times 3 plus -1 times 0 plus 2 times 1. So I just get 5. So that's the dot product of these two vectors. So this is a new operation we're going to be dealing with in this chapter and in the next few videos. So there are a bunch of easy properties, algebraic properties, the dot product satisfies. And the first one is commutativity. You can do the dot product in either order. You have this distribution thing where if you have a dot product of a sum of vectors with a second vector, then you can break it up. You also have this third property where if you multiply by a scalar, then you can multiply either of the vectors by the scalar first and then do the dot product. And the last one is if you do the dot product of a vector with itself, it's greater than or equal to 0. And if you actually get 0 when you do the dot product of something with itself, then that vector has to be 0 to begin with. Now it's pretty easy to see that each of these is true, and it all just goes back to the definition. If I think about the definition of this, it's obvious that the order doesn't matter, that this is commutative, because that just switches these entries, and multiplication is commutative. And similar with these other, if you just write down the formula, you can see that these things are all true. The next thing to look at, next simple definition, is the length of a vector, also known as the norm. If I have a vector, then its length is given by this formula. Now, this is really the length. If I think about a vector in R2, for example, let me take the vector 1, 1. Then, if I want to know the length of the vector 1, 1, well, I have this triangle, and it's a right triangle, and the side lengths are 1 and 1. So using Pythagorean theorem, I just get that this length is square root of 1 squared plus 1 squared. So I get square root of 2. And if you think about that Pythagorean theorem formula, that's exactly just this formula that we have here. So this length, the norm of this vector, is square root of 2, which really is the normal length that we're used to. And so that's true in 2 dimensions and 3 dimensions and whatever amount of dimensions you want. This norm really just gives you the length of the vector itself. And there are a couple of quick properties we can point out with this length. And the first one has to do with how it relates to the dot product. So if you take the norm or the length of a vector and you square it, so if you square this formula, well then the square root goes away. And what you're left with is just the formula for the dot product of a vector with itself. So this is a pretty obvious property, pretty easy to see if you just write it down, but it's pretty useful. This is used a lot to prove other things, so it's a good one to keep in mind. The second one is useful for computations. If you do a scalar multiple of a vector and take the norm, then that scalar you can pull out of this norm. But when you pull it out, you just have to make sure you take the absolute value of the scalar. This is a second property that's pretty useful. And again, if you just write down the definition of scalar multiplication and the norm, this should be pretty obvious to see. Now we come to the big definition in this video, and it's this orthogonal definition. So if I have two vectors in Rn, we say they are orthogonal if their dot product is 0. That's the way we define orthogonal vectors. Now you might want to think about, all right, what does this mean geometrically? Well, let's just see it in an example. And this is something that if you've seen Calc 3, you already know what it means. If your dot product is 0, you know what that means geometrically. but we're not assuming anybody has taken Calc 3. So we're just going to get this geometric intuition with an example. So here are two vectors in R2. And if I do their dot product, I get 1 times 1 plus 1 times -1. I get 0. So these two vectors are orthogonal. U and V orthogonal. Now if I draw the picture, I want to think about what they look like. I have this vector 1, -1, or sorry, 1, 1. And I have a vector 1, -1. And they're perpendicular to each other, geometrically. And it turns out, this is a general fact, and you could prove this fact, and this is proven in Calc 3, so I'm not going to do it here, but two vectors are orthogonal if and only if they are perpendicular geometrically. So that's the geometry behind this. This is one of the reasons why we like it. So U, V are orthogonal if and only if they are perpendicular. Here's the last definition I want to go through. So suppose you have a subspace of Rn, and let V be a vector in Rn that is orthogonal to everything in W, meaning geometrically it's perpendicular to everything in W. Well, then we say that V is orthogonal to W, to the entire subspace. Now, if I take all of the vectors that are orthogonal to W, if I take the set of all of them, then I put them together and I get what's called the orthogonal complement of W, and you denote it by W, a little perpendicular sign here, W perp, sometimes you call this. So let's see this in a quick example. I want to give you a subspace of R3, and we're going to try to come up with an orthogonal vector and the orthogonal complement. It's not so hard to do when you have the geometric picture in front of you. So here's what I want to look at. I want to look at all of the vectors in R3 where the x component could be anything, the y component could be anything, but the z component, my third entry, has to be 0. And if I draw that, that's just the xy plane. It's just the xy plane in R3. So here's W. It's just this flat plane in R3. Now let me take a vector in R3. Let's say it's 0, 0, 1. What I want to do is I want to show that V is orthogonal to W, meaning this is orthogonal to every single vector in W. Now it's pretty easy to check. All we have to do is take the dot product of this vector with every vector in here, and every vector in here looks like this. So we can see this pretty easily. Since 0, 0, 1, which is V, dot any vector in W, which looks like x, 0, 1, or x, y, 0, looks like, well, x times 0 plus y times 0 plus 0 times 1. Since every dot product is 0, we can say V is orthogonal to every vector in W, which means, by definition, V is orthogonal to W. So let me draw that. Here's my vector V. And so here I showed it algebraically. We just computed this dot product, but it's really easy to see geometrically. I mean, I have this picture, I have this xy plane. Obviously, if I take this vector, that's on the z-axis, this is perpendicular to the xy plane. It's perpendicular to every single vector in the xy plane. That's pretty clear. But now we go a little bit further. What is the orthogonal complement? What are all of the vectors, the set of all vectors that are orthogonal to W? What would they be? V is one of them. Can you find any more? Can you find all of them? So that's the next question. What is the orthogonal complement? W perp. And it doesn't take that long to realize that any vector on the z-axis, pointed up or pointed down, those are all going to be perpendicular to W. You can just see it geometrically. They're just multiples of V. They're just perpendicular to W. We could also see it algebraically. If I take anything on the z-axis, that just means this 1 is some other number. And that will be perpendicular to every single vector that looks like this. So the z-axis, anything on the z-axis is obviously perpendicular to W. And moreover, if I take anything not on the z-axis, let's say I took a vector like this would not be perpendicular to everything on W. And again, I could see it here just geometrically. This is obviously not perpendicular to the y-axis, for example. So it turns out that W perp is just the z-axis. It's the span of 0, 0, 1. So let me just fill that in here. There's W perp. It's just the z-axis. Now with this example, I could see some properties of the orthogonal complement. And that's the next list here. This is the last thing I want to mention, last basic idea. And I'm going to bring over this picture so we can see it in this picture. So I'm going to start with the subspace of Rn. In our last example, it was W, the xy plane. The first thing is the orthogonal complement is always a subspace of Rn as well. That's an important one. And to show this, we just have to show just go to the definition of a subspace. We have to show that the zero vector is in here, that this is closed under addition and closed under scalar multiplication. And it's doable and it's not that bad. I'm not going to go through that in this video though. But we can obviously see it in this picture, in our example. W perp was the span of V. It's just this line through the origin. That's obviously a subspace of R3. The next thing is, if I look at the orthogonal complement of the orthogonal complement, I get the original space back, which also should make sense intuitively. If I think about the orthogonal complement of W perp, I'm going to get all the vectors orthogonal to the z-axis. And well, those are just all of the vectors in the xy plane, which was the original subspace I had. The next one is if I take the intersection of W and W perp, if I look at all of the vectors that these have in common, there's only one, and it is the zero vector. And you can see it here. These intersect in the zero vector. These are both subspaces, so they both have the zero vector, of course. But since they're perpendicular to each other, they're not going to have anything else in common. The last one has to do with dimension. If I look at the dimension of W and I look at the dimension of W perp, these are subspaces, so I could talk about dimension. Then when I add them up, I get n. I get the size of Rn that I'm in, and that's obviously true in this example because I'm in R3. W has dimension 2, W perp has dimension 1. When I add them up, I get R3. So there are all the basics of orthogonality. The definition, this idea of orthogonal complements, and the inner product and everything. In the next video, I'm going to talk about orthogonal projections, which is another thing that if you've taken Calc 3, you've probably seen already. But I'm going to go through the basic definitions, and the goal is to use that for some important things, which we'll see.